Step outside on a dark, moonless night in the northern hemisphere, and you can spot a faint, nebulous smudge hanging in the sky. To the naked eye, it looks like a delicate patch of glowing gas. For centuries, astronomers viewed this smear of light as a nebula, a local gaseous cloud drifting quietly within the boundaries of our own Milky Way. This classification dates back as far as the Persian philosopher al-Sufi in 964 AD. Well into the early 20th century, the scientific consensus held that the Milky Way was the entire cosmos. Every star, every planet, and every cloud of dust we could observe was thought to be contained within our single galactic home. This assumption created a comforting, highly contained view of our place in space. We believed our cosmic neighborhood had a fixed local boundary, leaving humanity unaware of the massive scale of the void sitting just outside our stellar backyard. The scientific establishment fiercely defended this single galaxy model. During the Great Debate of 1920, leading minds like Harlow Shapley refused to accept that spiral nebulae could be their own island universes, arguing that the mathematical distances required for such a scale were too vast to exist. That comforting illusion broke 4 years later. In 1924, American astronomer Edwin Hubble pointed the Hooker telescope in California at that fuzzy smudge and identified something highly specific inside it: pulsating Cepheid variable stars. This animated diagram tracks how these pulsations translate into distance. A Cepheid variable's pulsation speed directly correlates to its true luminosity. By measuring how fast the star blinks, astronomers determine its actual brightness, comparing it to how dim it appears to calculate its position. When Hubble ran the numbers, the math placed the stars at an impossible distance, over 1 million light-years away. Hubble's data confirmed that smudge was the Andromeda Galaxy, a separate colony of stars situated deep in the void. These calculations shattered the claustrophobic universe model overnight. By proving that other galaxies existed far beyond our own, the known scale of the cosmos multiplied by millions, forcing humanity to realize we were just one tiny island in a deeply populated ocean. Today, more precise measurements place Andromeda even further away, at 2.56 million light-years. To truly understand our neighbor, we have to cross that sprawling intergalactic void, arriving at a structure far more intimidating than our own. Andromeda is a physical behemoth. It boasts an extended stellar disk stretching 220,000 light-years across, housing a population of over 1 trillion stars. It dwarfs the Milky Way in almost every measurable metric. Its massive size and complicated spiral arms are the direct results of a 10-billion-year history of aggressively consuming smaller galaxies. The forensic evidence of this galactic cannibalism is floating right in Andromeda's outer halo. Small satellite galaxies like M32 and dense star clusters like Mayal 2 are the stripped, dead cores of ill-fated protogalaxies that strayed too close and had their outer layers absorbed by Andromeda. Andromeda stands as the dominant predatory apex structure of our entire local group. To see the impact of that violent past, you have to look deep into Andromeda's center. Unlike the smooth core of the Milky Way, Andromeda features a peculiar, fractured double nucleus. Hiding inside the darker of those two dense stellar clusters is an immense gravity engine, a supermassive black hole possessing over 100 million solar masses. This chart compares the core of our galaxy to theirs. The Milky Way's central black hole, Sagittarius A star, sits at 4 million solar masses. Andromeda's black hole is over 100 million solar masses, an order of magnitude entirely outside our local league. This oversized black hole serves as the ultimate receipt of Andromeda's history. Over billions of years of mergers, it has continuously bloated itself by feeding on the gas and matter of the galaxies it has devoured. As a general rule, the universe is actively expanding. Because of this, the vast majority of distant galaxies we observe in deep space are constantly moving further and further away from us. We know this because of the Doppler shift. When an object travels away from an observer, the light waves it emits stretch out, shifting toward the red end of the spectrum. Most of the cosmos is distinctly redshifted, but as this animation shows, the light coming from Andromeda does the opposite. Its light waves are tightly compressed into the blue end of the spectrum. A blue shift means the object is hurtling directly toward the observer. Andromeda is currently barreling toward the Milky Way at 110 kilometers per second. While universal expansion pushes the broader cosmos apart, our two galaxies are simply too massive and too close to each other. At this local level, the raw gravitational attraction between the Milky Way and Andromeda completely overpowers the outward expansion of the universe. The 2.56 million light-year gap Hubble discovered in 1924 is a temporary state, a distance that is currently and rapidly closing. Over the next few billion years, that faint smudge will steadily grow in the night sky. Eventually, it will expand until its glowing core and dusty spiral arms dominate our field of view, appearing larger than the Moon. In 4 billion years, the two titans will finally collide. The immense gravitational forces will irrevocably deform their spiral shapes, whipping long, chaotic tails of gas and hundreds of billions of stars deep into intergalactic space. While individual stars rarely hit each other directly, the gravitational havoc will shred finely balanced planetary orbits. Entire solar systems will be forcefully ejected into the void, while others will be flung inward, ripped to pieces as they pass near the chaotic, shifting galactic core. By year 7 billion, the final stage takes hold. The two supermassive black holes will violently merge, binding the surviving stars into a single, massive, structureless elliptical galaxy, known as Milkomeda. Having exhausted all the star-forming gases from both original galaxies, Milkomeda will have no materials left to build new stars. Over the span of tens of quadrillions of years, its aging stellar population will slowly cool, freeze into solid spheres of matter, and eventually go entirely dark. Humanity exists in a brief, luminous window of cosmic time. We get to study the mechanics of our universe, knowing that the Milky Way's entire existence is inextricably tied to the violent trajectory of that fuzzy smudge first noticed in the ancient night sky.